Okay, in the last video, I covered the absolute basic definitions of sets, set theory, and we talked about Russell's paradox. So in the class, we are going to be working with sets all the time, and it's probably the case that everyone in this class should have seen a lot of the basics of set theory. I'm going to try to mix in things like Russell's paradox and at least one other cool theorem so that in the course of recovering what I expect you already know, you'll at least get to see or re-see some fundamental ideas. I'm also going to try to cover sets in a way that points us to some higher math. And but in order to dig in and actually get to work on them, the first thing we want to start thinking about are operations that you do on sets and relations that hold between sets. So the basic relation that in some sense defines sets is a membership, and from membership you get subset. So remember that this is written as follows: a set A is a subset of a set B. This is true if and only if for every element of A, that element is also in B. All right, so every element A in A, and really I should put for every element A in A, we have A is also in B. Okay? Now, you may sometimes see this without the little underline here, and that would be a strict subset. So if you see that, if you see A subset of B, this means, this is true if and only if A is a subset of B, and they're not the same. But I have to be a little bit careful because I haven't actually told you what it means to be the same. I'm going to save that for down here. So subset, in a way, is the extension of membership to entire sets. Superset is just the opposite of this. So we're going to say that A is a superset of B. That was terrible. Let's try that again. We'll say that A is a superset of B. We don't write this one very often. If and only if B is a subset of A. Okay, so this is just writing it the other way around, which is sometimes useful because these kinds of statements, right, like A is a subset of B, if you notice that when I say that, it's a complete sentence, and sometimes we would prefer to be talking about the set A, talking about the superset as the subject of that sentence. So it's handy to have another relation to do this, but you could get by with just one. Now, I'm going to say that equality of sets, well, it means that they have the same elements, and it's not usually defined this way, but you can think of it, the definition as just meaning that A is a subset of B, and this is an if and only if here, A is a subset of B, and B is a subset of A. So the reason it's useful to have this kind of definition of equality in terms of subset in both directions is that most of the time when you're trying to prove that two sets are equal, you actually have to do it in two steps. Because the set is defined in terms of membership and the subset is more naturally expressed, is a more natural kind of extension of membership. Usually what you show is that, well, first you show that one of the sets is contained in the other, and then vice versa. And so having these two claims be the definition of equality gives you a head start on anytime you're trying to prove that two sets are equal. In fact, it's one of the basic hints if you're stuck, you know you're supposed to prove that two sets are the same and you don't know where to start, you just pick one and try to prove it's a subset of the other one. And then you do the other way. Okay, so these are subset, superset, and equality. Now, just remember, of course, that the sets are not ordered, so it's just a matter of whether or not the membership holds. So if I were to write something like 1, 2 as a set equals 2, 1, this is absolutely totally true. right? Because for every element over here, it's an element over here. So 1 is in this set, 1 is in this set, 2 is in this set, 2 is in this set. So this set is a subset of this one, and then I could repeat it the other direction to show the equality. Very basic stuff. All right. All right. So a lot of standard operations that we're going to do on sets, we have pretty standard notation. It's funny, if you ever read any really old math texts where before some of these notations were standardized, they can be tremendously frustrating because it was a kind of a wild west of notation. People would make them up on the fly. The basic operations that everyone should know, of course, are what? Union and intersection. These are kind of most common operations on sets. Now, A union B is the set of all things that are either in A or in B, or in both. Intersection, A intersect B, it's the things that are in A and also in B. So you could think of this as the kind of or, and this as a kind of and there's a strong relationship here to those logical operators, and that's why even there's a relationship in the standard notation where you see or written as the sharper version of this, and as the sharper version of the intersection symbol. So union is the intersections, okay, standard. One we're going to use a lot is set difference or set minus. Now, this one is a weird operation because you can subtract something that's not there. Usually when you do subtraction, say in elementary school arithmetic, and you're going to subtract one number from another, well, the other number kind of contained the number you were starting with. Even if it ends up negative, you can it still feels like you're removing something that was already there. Or if it wasn't there, you end up negative. So you were subtracting something that was somehow there. In the case of sets, you can subtract a set that doesn't even intersect the set that you started with. And that's totally okay. Let's see it in action. So if I write A set minus B, this is equal to the set of all elements A in the set A, such that A is not in B. Okay, so if there were any elements in B that were also in A, we've removed them to get this difference. So it should be immediately clear that A minus B is not usually equal to B minus A. I'll leave it as a little exercise if you can think of some sets where this actually holds. What do you think? What's some simple ones? I wrote this as if it's a fact, but maybe we should take a quick sanity check. Can you think of an example of sets A and B for which A minus B is equal to B minus A? There's some really easy ones. I think the easiest is probably if A is equal to B. Is that the only case? Let you think about that. Leave that as an exercise. All right, so set difference is one that we'll use. One that's not a standard set operation, but it's kind of useful to think about in terms of logic would be the complement. So this one, you have to be careful because it's always relative to some subset. So if I have A as a subset of B, then I can define, A is a subset of X, I can define a complement in X to be X minus A. Now, you have to be really careful about this because as a notation, it's weird. As a notation, if I just wrote a complement, it doesn't mean anything unless I know what X is. Okay, so I have to actually know what set I'm taking that A away from. But if I do, then it makes sense, and that's why complement sort of behaves like not, and that's why it also has this same notation that's often used for logical negation. So that would be set complement. All right, there is another binary operation on sets, which I think is very useful. And we'll get to it some more. Oops, not this one yet, not the Cartesian product yet. Let me get a new sheet of paper here. So there is this other operation that's useful, which is the symmetric difference. And symmetric difference, if you want to kind of keep this analogy with logic, symmetric difference sort of looks like XOR. In fact, we'll even use an XOR-like notation. So A plus symmetric difference with A and B. This is going to be all the things that are in A but not B, and B but not A. So it's symmetric, and it's basically making this difference operation symmetric by taking A minus B union with B minus A. And just in words, if you hear me say minus, right, that's me describing usual set difference, and I will say the symmetric difference for this kind of XOR operation. And you can see just in action, if I took sets like 1, 2, 3, and symmetric difference with a set like 2, 3, 4, this would be equal to, well, the first set minus the second one. It's going to be left with just the 1. And I union that with a set, which is the second set minus the first one, which is also has the 2 and 3. It's going to be just the 4. So the union of those two is the set 1, 4. Okay, and the Venn diagram picture of this one would be something like the following. Right, it's the union minus the intersection, and I'll leave that as a little exercise. If we use this as the definition, you can prove that a set symmetric difference with B is equal to A union B minus A intersect B. And I'll leave that as a little exercise to do, just to make sure that you understand basics of sets. All right, another very important operation is the Cartesian product. So if I have two sets, the Cartesian product of those two sets is going to be the set of ordered pairs. So it'll look like this, A comma B, such that A is in A and B is in B. Okay, so if A were equal to 1, 2, and B is equal to 4, 5, 6. Okay, I've got myself a big task here. Hopefully I have enough paper. Maybe I'll use a thinner pen just to fit it all in. That one doesn't work. Let's get one that works. Don't have one that works. Okay, A times B is equal to, right, it's going to be a set of pairs. So it's 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6. Does it fit? And I fit my curly brace in there. Oh, just barely got it. Okay. Hopefully that's readable. Hopefully you understand the Cartesian product. Sometimes, actually often, the Cartesian product is used for more than just two sets. So you might see things like A times B times C, in which case this gives you triples of elements, right, where the first one's in A, the second one's in B, and the third one's in C. This is a little bit strange, especially if you're computer scientists and you want to think about this operation as being parsed in some order, because this is considered an associative operation that somehow you can take the pairs here and then pair them with this. But of course, you don't get things that look like A, B, C. When you do a three-way Cartesian product, you get something that looks like A, B, C for A and A, B and B, and C and C. Now, this is a notational, actually, well, this one would give you this, but this one gives you this. Sets of things that look like this. All right, so the Cartesian product is a standard way that we're going to go and take sets and combine them to make new sets with more elements. And one other little notation that I'm going to use is that if I have a set, S, I might write S choose 2 to be the set of two-element subsets. So if this was a number here, if like it was n choose 2, we would be really comfortable thinking of that as another number, right? It would be the number of two-element subsets. Here, the actual subsets will be these two-element subsets. And I can fit a very, very small one in here if I were to take, say, 1, 2, 3, choose 2. That would be, oh, maybe I don't fit it. I won't be able to fit it. It's going to be too big. It's still 3 elements. Maybe I can do this. Let's see. It's a set containing 1, 2. 1, 3, and 2, 3. Okay, and pulling out subsets or collections of subsets from a set is a very common natural thing that we're going to do. And actually, if we want to do it in a complete way, that is, if we want to get all the subsets, we end up with something called the power set. So if S is a set, then the power set of S, which you'll sometimes see written as 2 to the S. This power set of S is defined to be the set of all subsets. So it would be we might just write it like this. We have to be just, again, a little bit careful here. If S is infinite, we actually need the axiom of choice to believe that this always exists. But for nice finite sets, it's really clear. In fact, you can even write it out. And if you did write it out for a finite set, you would see that the number of elements would be something like 2 to the size of S. And that's why we get this notation. Incidentally, it's also why we have the notation S choose 2, because again, this notation is, if I were to ask for the size of this set, which is the number of elements or the cardinality, it would be the size of S choose 2. Although, we have to be careful in the case of infinite sets. All right. One other notation that I'm going to use quite a bit is a notation for sequences. Now, it can be a little bit tedious to constantly write things like 0, comma, dot, 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 comma, n to refer to the numbers from 0 to n. Instead, I would refer to this sequence as the following, square brackets. I could do it a couple ways. One simple way would be 0, colon, and don't be alarmed, but I'm going to put an n plus 1 here. And this idea that a sequence of numbers separated with the first element given before the colon, and it goes up to but not including the element after the colon. This is totally common if you're used to writing, say, code in Python. This is a really good technique. I'll give you another example of why. But I also might shorten this. I might just write colon n plus 1, which is also something you will see in Python. If there's nothing before, just assume it starts at 0. And I may at some time forget entirely and just write n plus 1, but you'll correct me. All right, why is this a good thing to do? Well, if I write this n plus 1 instead of n or anything else, it's clear that that tells me how many elements are in this set. So I have a set that's a sequence of integers that has this many elements. Also, wonderful things happen by leaving out the last element. For example, if I took A to B, and I take the union of that with B to C, then I get, well, A to C. Also, it's very easy to check the length of such a sequence, A to B. The length of this sequence is just equal to B minus A. You don't have to do any of this extra like minus 1 or plus 1. It sort of takes care of it automatically for you. Makes it very clean. Yeah, so this first one, let's write it out. Now, there's a bunch of other, I guess there are a bunch of other cases where you'll find this notation really, really useful. But this connection to writing Python will also become important for us, and especially if I give little examples in code. All right, so that is how I'm going to describe integer sequences, and I know that it is going to be, it is a little different than what you're probably used to seeing. Most math textbooks won't do this, but also most math textbooks will be inconsistent between them about whether or not 0 is included or not. So we're going to stick with the Python convention, and that way when we switch to code, it'll be a really easy transition.